Good evening, everybody. Welcome to today's week 8 session on aircraft design. So, in this week, Professor has taught, he has mainly solved one numerical on wing loading. So, he has revised previous week's content and he has uh, solved one numerical on wing loading. And then he has discussed some stability considerations when designing an aircraft, but he did not discuss it in detail. Okay, so this is mainly next week's topic, but he discussed this stability considerations in brief. So, like as you know that you know thrust, power, and wing loading. So these are the definitions. So thrust loading is T by W, power loading is W by HP, and wing loading is W by S. And these are the uh, thrust to weight ratio and horsepower to weight ratios for different kinds of aircrafts, and I have taken this table from Raymer's book. Raymer's book. So when you calculate, like I will revise the previous week's content. Okay, in over here, I will revise it in brief. Then I will also solve that numerical which sir has gone through, and then we'll do some exercises. So W by S for maneuvers. So there are two kinds of maneuvers. One is your instantaneous maneuver, and the other one is the sustained turn. So basically, what happens is that when the aircraft is turning, the lift vector is pointed to the side. Okay, and that lift which points to the side, that causes the turn. So if I draw a like a forward view of the aircraft, then you can consider an aircraft like this. Okay, with the wings and the tail. So so normally it flies like this and the lift and weight are balanced, but when the aircraft is turning, the lift vector is pointed off to the side, but the weight obviously still acts downwards. So this offset lift vector, this causes the turn. Now if the turn is not properly managed, then what happens is that the aircraft loses altitude and velocity when it is turning. So instantaneous turn rate is the maximum possible turn rate where we do not care about losing speed or altitude. So let me repeat this again. So when an aircraft is turning, it tends to lose altitude and speed, and to compensate for this, we have to increase the thrust. Okay, so we have to increase the thrust. We might also have to increase the angle of attack. But instantaneous turn rate is the maximum possible turn rate without caring for loss of altitude or velocity. And so this is mainly limited by the structural structural limit of the aircraft. So uh, a aircraft with a stronger structure can take a tighter turn. So here this diagram is called a VN diagram, and you have learned about this in the performance course. On the y-axis you have the load factor N, and on the x-axis you have the velocity V. So this solid line over here, this shows the maximum possible turn rate at any specified velocity. Okay, so sorry, not the turn rate, the maximum possible load factor at any possible velocity. Now you will see that at any velocity, let us say 100 miles per hour, above a certain load factor, the aircraft cannot fly. because this area indicates stall, so the aircraft is unable to produce a higher load factor. Okay, so this area is not suitable for flying. Uh, but if you fly at higher velocities, you can fly at higher load factors. Okay, but this is up to a point. After a point, the aircraft may suffer structural damage. So that is the maximum load factor it can fly at. Similarly, there is a maximum velocity the aircraft can fly. Beyond that velocity, so over here, beyond that velocity, the aircraft will suffer structural damage. Okay, and the engines may not be able to produce thrust to take it up beyond that velocity. So this is the maximum load factor and maximum velocity. So when you combine these factors, you get something called a corner velocity. The corner velocity is the minimum possible velocity where you can fly at the maximum possible load factor. So in this case, if the maximum load factor is approx 7.5, then corner velocity is the minimum possible velocity where you can fly at 7.5. Okay, and usually when in a fighter aircraft, they try to fly at the corner velocity so that they can take maximum possible turns. They can sustain maximum turn rates. So usually you can calculate the maximum turn rate from this Venn diagram, or your turn rate may be given as part of a specification. So from the turn rate, you can use this formula to get the load factor. Now finally, when you have the load factor, you can calculate W by S using this formula, QCL max by N. Here Q is the dynamic pressure. Okay, now moving on. So similarly, you can also calculate the wing loading for a sustained turn. So if you see that the for a instantaneous turn, the equation is lift equal to NW. For a sustained turn, you have lift equal to NW and thrust equal to weight. So thrust equal to drag. So because of the second condition, that thrust equal to drag, the aircraft, it does not lose altitude or speed. So if the aircraft is tilted like this is the lift. So here if you write the equations for a sustained turn, you will get lift cos theta equal to weight, and thrust equal to drag. So lift is also equal to n weight. So NW cos theta. So n is equal to 1 by cos theta. Now, so you can get an idea of n from this relationship. Otherwise, what you can do is that you know that thrust is equal to drag, and you can expand the equation for drag. So the uh, way all of these equations are derived is we write thrust equal to drag, and then we write drag as qs cd naught plus kcl square. We also write lift equal to nw, and the lift we can write it as qs cl. Then what we do is we find cl from here, cl equal to something, and then we substitute this cl in this equation, drag equation, and that is how we get the relationship between thrust to weight and wing loading. So here you have substituted in place of drag, you have done all these manipulations over here, and then you can divide by the weight to get this relationship. Here you will see that the wing loading comes both in the numerator and denominator. So what happens is that when you expand this equation, you get a quadratic equation in terms of W by S. So you get some terms into W by S square plus again some terms into W by S plus a constant term equal to 0. And then you can solve it using the quadratic formula to get this equation for sustained turn rate. Over here you will see one thing, that the term in the square root, it has to be positive. So from there we can get this relationship, that the thrust thrust to weight ratio should be greater than equal to 2n root over CD naught by pi aspect ratio E. Moving on. So similarly, you can derive the equations for climbing and gliding. Okay, so for climbing, we have to write it like so. For climbing, you can draw the free body diagram, and if you expand it along this thrust and drag axis, you get and then if you manipulate this equation, you get thrust minus drag by weight equal to sine gamma. So this sine gamma is, they're calling it as the climb gradient G, and sine gamma is also equal to the vertical velocity by the flight velocity. So you can write G as this, and then you can rearrange it to get this equation. And the drag, so the drag to weight ratio, it is like as you saw in the previous slide, so it becomes like this. Okay, same equation over here. And if you compare from the previous slide, okay, so if you compare from the previous slide, you will see that uh, in the previous slide the equation was thrust equal to drag, and then you can divide by the weight, and then you can expand the drag using this formula to get the this relationship over here. Now over here for climb and glide, in the left hand side, instead of T by W, we have T by W minus G. The rest of the things are same. So, and also here n equal to 1. Then if you solve for W by S, you get this relationship over here. You get this relationship, which is same as the previous one. But you will see that T by W has been replaced with T by W minus G. And also the load factor is 1. Now this equation which we derived here, it can also be used for gliding flight. Uh, for gliding flight, what we do is we put T by W equal to 0, and we and the glide ratio is some negative value. Okay, we put a negative value. Why? Because during gliding the uh, angle gamma is negative, so sine gamma will be negative. We can also use this to find the wing loading for uh, absolute ceiling and service ceiling. So in that case, we substitute G equal to 0. Now from here also you can find a relationship. Okay, uh, the term inside the square root, it has to be positive. So you get this condition that the thrust to weight ratio is greater than equal to the climb gradient plus 2 root CD naught by pi aspect ratio E. So here you will see that G is sine gamma. Hmm. So we have actually derived this relationship from another way also. If you remember that you can write this equation. Okay, you can write this equation, and then from here if you divide by T by W, you get T by W equal to sine gamma plus 1 by L by D. So from this relationship also you can see that the thrust to weight ratio, it has to be equal to sine gamma at least. It has to be more than sine gamma. So you can see that both the approaches they give a same kind of relationship. Now moving on. So next we have the wing loading for cruise flight. Now no, ignore this section. This is for the maneuvers. Now, wing loading for cruise flight, you know that there are four combinations, like four types of cruise flight. You can have jet, propeller, and you can be optimizing for range or endurance. So here I will discuss CL. What is CL? Okay. So for propeller planes, it is CD naught by K. For jet, if you want to maximize for range, it is CD naught by 3K. And for jet, if you want to maximize endurance, it is CD naught by K. And for this, it is 3 CD naught by K. So these are the CL values. Now, what you simply do is, uh, you know the equation for uh, cruise flight. It is lift equal to weight and thrust equal to drag. So what you simply do is, you substitute this in this equation. So you write W equal to lift equal to QS CL. Okay, and then you can divide by S to get W by S equal to QCL. Okay, and then in place of CL you can substitute these formulas, and by simply doing this you will get the wing loading for cruise flight. You will see here that Q is put over here, and the rest of the terms, they are just CL. If you calculate it, you will see that it is just CL. Now moving on, so now we have to discuss the thrust to weight ratio and the wing loading for takeoff. So for takeoff, you know that the takeoff velocity is 1.2 times the stall velocity, and the stall velocity is given by this relationship. So you know that QSCL max. So stall velocity is the minimum possible velocity an aircraft can fly. So QSCL max will be equal to the weight, and with this then you can wait. Stall velocity is the minimum possible velocity the aircraft can fly at. So you can write weight equal to lift equal to half rho v square s CL max, and then from here you can solve for Vs. You will get Vs equal to, this is stall velocity and the takeoff velocity is 1.2 times stall velocity. Now you can draw a free body diagram of an aircraft on the runway, and you can draw the forces. So you have thrust, then you have lift, you have weight, and you also have drag, and you also have rolling resistance or friction provided by the wheels. Okay, and then you can write it in this form, like the net force. So F is the net force. It is equal to thrust minus drag minus friction coefficient into normal force, and normal force is weight minus lift. Okay, so the rolling resistance is equal to friction coefficient into normal force, and the normal force is weight minus lift. Okay, so the net force is equal to the mass into the net acceleration. Further, what you can do is you can multiply and divide by g. So m dv by dt, right? M dv by dt. You can multiply by g here, and you can divide by g. So then this term becomes the weight. Okay, this term becomes w weight, and this term, it is acceleration by g. Okay, so, and then you can rearrange everything to get this kind of a equation. So this is how, like, the g term comes into the picture. Okay, by this manipulation. Also, to write this equation, we have to use a physics relationship, that v square minus u square is equal to 2as, where v is the final velocity, u is the initial velocity, a is the acceleration, and s is the distance. So during takeoff, the initial velocity is 0, so this is equal to 0, and v is the takeoff velocity, and a is the average acceleration, and s is the takeoff distance. So now you will see that the force, net force, and hence the net acceleration, it varies during the takeoff roll. Okay, so it varies during the takeoff roll, but for simplification, we consider an average acceleration, and the average acceleration is evaluated at zero point 0.7 takeoff velocity. So at zero point 0.7 takeoff velocity, whatever drag and lift we are getting, we use that to calculate the average acceleration. And once we have that, then you can calculate the takeoff distance. So from this you will get S is equal to V square by 2A. So S is equal to V square by 2A. So the rest of the terms are basically just the acceleration terms. Further, in case of VLO, you can substitute this formula and you can get this relationship. Okay, SLO equal to 1.44 times W square by all this. And you can further simplify it. You can assume that the contributions of the drag and the friction are negligible compared to the thrust. So the contributions of these terms, they are less than 10% of the thrust. Okay, so in, like, for a first approximation, you can ignore these terms. Okay, and you can only consider the thrust term, and then you will get this kind of relationship. So you see that the takeoff velocity, it depends on the square of the weight, okay, but otherwise it inversely depends on the air density, the wing surface area, the CL max and the thrust. So if you take off from a lower altitude which has a higher air density, the takeoff distance is lower. If you use a larger wing, if the wing surface area is more, then the takeoff distance is lower. If you use a higher CL max or a higher thrust, then also it is lower. But if you increase the weight of the aircraft, then the takeoff distance increases, and that too quadratically, not even linear. Okay. Over here, there is one other manipulation you can do. So you can write uh, rho by rho naught into rho naught. So, and this rho by rho naught, you can write it as sigma rho naught. And here rho naught is the air density at mean sea level, which is 1.225 kg per meter cube, and this is constant. So if you do that, then the equation becomes SLO. Okay, so this is the equation. Now in this equation you will see that these terms are constant, whereas these terms are actually variable. So these terms are variable, but the rest of the terms are constant. Okay. So there has been some statistical data which has been collected for the takeoff distance and this parameter W square by rho S CLT. So this parameter is also known as the takeoff parameter. So TOP is W square by rho S CLT. Okay. So this is the takeoff parameter, and some data has been collected for SLO versus takeoff parameter. So we can use this statistical data to get a first approximation of the uh, wing of the parameters. Like if we, so you will see that the takeoff distance, it depends on the wing loading also and the thrust loading also. So if we know one of the quantities, like if we know the thrust loading, then using the takeoff parameter we can find the wing loading. Okay, so if one, so over here it is given like this. So if you know the thrust loading, then you can use this formula to get the wing loading. Okay, if you know the wing loading, then you can get the thrust loading. So in this way you can use the takeoff parameter. So this is some statistical data which I have taken from Raymer's book. So it plots the takeoff parameter and the takeoff distance. So on the x-axis we have the takeoff parameter. So you will see it is wing loading by rho CL and thrust loading. And on the y-axis you have the takeoff distance. So you see that it is almost like a linear relationship. So let us say that takeoff distance is given to you as part of a specification, then you can take the takeoff distance, okay, like this. You can extrapolate it, and then you can drop it onto the x-axis to get a idea of the takeoff parameter. And then once you have the takeoff parameter, so in this case I am taking SLO has 6 into 10 to the power 3 feet. So from here we can get the takeoff parameter as something approximately 320, approximately 320. So once we know that the takeoff parameter is 320, we can use these equations to find the wing loading or the thrust loading. Now moving on, so professor has also discussed about high lift devices. So you know that the during takeoff and landing, the takeoff and landing velocities are mainly dictated by the stall velocity, and the stall velocity is inversely proportional to the CL max. So during takeoff and landing, there are mechanisms to increase the CL max of the wing. So they are done with the help of high lift devices. So they are mainly of two types. One is flaps and the other one is slats. So flaps are installed at the trailing edge, whereas slats are installed at the leading edge. So the flaps, they increase the camber of the wing, and they may also increase the wing surface area. So both of these mechanisms, they contribute to increasing the CL max. And also some of the flaps may have a slot. So over here there is a slot, so air can flow through this slot. Okay, here there are two slots, and here in the slat also there is a slot. So it has been shown that these slots, they increase the lift of the wing even more. So flaps and slats, like, they increase the lift, and the slots also increase the lift. So all of these effects, they contribute a lot to increase. But you know that if the lift increases, but along with that the drag also increases. Now I'll discuss briefly the wing loading for approach and landing. So for approach and landing, we'll use a statistical relationship, which is that the landing distance is approximately equal to 0.35 into approach velocity squared. So VA here is the approach velocity. So it has been shown that S land is approximately this. Now the approach velocities can be further written as 1.3 times the stall velocity. So approach velocity is approximately 1.3 times the stall velocity. And you know that the stall velocity can be written in this fashion. So Vs is, so then what you can do is you can expand this equation and you can solve for W by S. So you will get that W by S is equal to W by S will be half rho V square CL max. And then the stall velocity, you can find it from this equation. So you can write Vs is equal to Va by 1.3. So when you write that, you will get this equation. So from here you can estimate the wing loading for approach and landing phase. Once you have the wing loading for all of these phases, then you have to see that which phase of the flight you have to give priority to, because from all of these phases of flight you will get different values of wing loading. You will get different values of wing loading, and then you have to see that which value or which phase of flight you are giving more priority to. So now I will discuss an example, uh, which, like, I've taken from Raymer's book, and also, like, sir has discussed this also, but I'll further discuss it. So you will find this at the end of the book. At the end of the book, there are he has designed he has gone through the whole aircraft design process for two kinds of aircrafts. So in this first kind of aircraft, uh, they want to build a single seat aerobatic aircraft, and So the engine is given, okay, engine is given, and the design goals are given. So these are your mission specifications. So performance will be between these two planes. These are two aircraft, so the performance will be between these two. And you can see that V max is greater than 130 knots. V stall is less than 50 knots. So you can write that Vs is less than equal to 50 knots, and the takeoff distance is less than 1000 feet. And here we are using the 50-foot obstacle limit. So SLO, rate of climb is greater than equal to 1500 feet per minute, and range is greater than equal to 280 nautical miles. V cruise is 115 knots, and the maximum load factor is plus 9 and minus 6 G. Okay, and this is the mission profile. This is the mission profile. From here you can also find that the cruising altitude is 8000 feet. Okay, so then so there are many, he has designed many of the aspects of this aircraft, but I will go through the key sections only. So then he has discussed about the wing geometry selection, where he has selected the aerofoil also. So from here you can see that the aspect ratio is 6. So for the wings, the aspect ratio is 6. This is the wing sweep and the dihedral. Then this is the aerofoil, and there is no twist. And these are the specifications for the tail. So not very important for this discussion, but and then he has selected so this is a propeller built aircraft. So he has selected the horsepower to weight ratio, and horsepower to weight ratio. So using like by looking at other aircrafts of the same type, so these are some other aircrafts of the same type. So from here you can get a idea that the horse weight to horsepower ratio or the power loading, tentatively you can select it as 8. Okay, so this is some statistical data, but here tentatively select the weight to horsepower limit as 8, and the W naught as 1200 pounds. So you can, now we will calculate the wing loading for uh, all the different phases of flight. So first you can look at some other aircraft of this type and you can see what is the wing loading. So you can see that the wing loading of all these aircrafts are uh, on the order of 10. So it is 10 plus minus uh, 10 plus minus 3. Okay, so of this order. Okay, now so first let us calculate the like what is the wing loading at stall. Okay, wing loading at stall. So here first we have to know the CL max. Okay, and he has assumed here that there are no flaps. So to calculate CL max, so he has used this formula. So he has used CL max is equal to 0.9 CL max. So actually, like, this is the 3D CL max and this is the 2D CL max. So if you remember from here, from the previous page, over here he has selected the aerofoil. Okay, and then after selecting this, you can also find out what is the CL max of this aerofoil. So the CL max comes out to 1.2. So this is the 3D CL max. It comes out to 1.2. Then what you can do is you can put it into the stall equation. So the will be 1/2 rho v square CL max. So you can substitute all these terms, which is half, and then rho at sea level you can take it as 0.00238. V, if you remember, Vs was 50 knots. So Vs was 50 knots. Feet per second, and the CL max is 1.2. So from here you get that the wing loading is 10.2 pound per foot square. Now for takeoff condition, okay, for takeoff condition, first he has calculated the takeoff parameter. Okay, so you can calculate it from using the historical data. So the takeoff distance is 1,000 foot, and he is using the 50 foot obstacle limit, and this is a single engine propeller aircraft. So if you go to this relationship over here, so we are talking about this propeller aircraft over here and 50-foot obstacle limit. So let us see what we get for 1,000. So for 1,000, the takeoff parameter is approximately, like, it is a little bit over 100. Okay, it is approximately 120. Okay, so you can see that he has taken the takeoff parameter as 120 from the chart. From the chart, he has taken the takeoff parameter as 120, and then you have to calculate the CL at takeoff. So over here, he has used this relationship that the weight of the aircraft will be same only. Okay, so at during stall and during takeoff, the lift will be balancing the weight, right? So the weight is equal to the lift at stall, and it is also equal to the lift at takeoff. Okay, so the lift at stall will be half rho v square s CL at stall, and this is equal to half rho v square uh, s CL at takeoff. So if you cancel all these common terms, then you get Vs square CLS equal to VTO square CLTO. So from here you can find CLTO, which is CL max into V stall by V takeoff square. and now V takeoff is equal to 1.1 times V stall. So in this problem he has assumed that takeoff velocity is 1.1 times stall velocity. So with this you can get the takeoff CL is 0.99. So CL takeoff is equal to 0.99. Now if you remember what is the takeoff parameter, takeoff parameter is wing loading. Right. The takeoff parameter is wing loading by sigma and CL and the power thrust loading HP by weight. Okay, so this is the relationship. So in this formula now you know that what is the takeoff parameter, it is 120, and you can write, you can assume that you are taking off from sea level, so sigma is 1 and CL as we calculated it is 0.99 and HP by W. So tentatively if you remember from the previous page over here, we have selected weight by horsepower as 8, so you can substitute here 1 by 8, and then from all this you can calculate the wing loading. So the wing loading comes out to 14.9 pound per foot square. Next we'll look at the climb performance. So for the climb performance, so first we calculate what is the climb gradient. So here he has assumed that the climb speed is 70 knots. So V is 70. Okay. So then you can calculate the climb gradient as vertical velocity by velocity. Okay. And the vertical velocity was given here as a specification. If you see, it is 1500 feet per minute. So therefore G will be 1500 by 60. Like the numerator is now in feet per second, and the climb speed is 70 knots, so 70 into 1.689 feet per second. So with this you get that the climb gradient is 0.212. Now you calculate the thrust loading. So if you remember that the for a propeller aircraft the equivalent thrust loading is calculated using this formula. Uh, So you can use this formula to calculate the equivalent thrust loading. So this is the propeller efficiency factor, and this is the velocity, and this is the horsepower to weight ratio. So 550 into propeller efficiency is assumed to be zero point 0.8, and climb velocity is 70 knots. So 70 into 1.689 feet per second, and horsepower to weight ratio is 1 by 8. So with this you get that the thrust to weight ratio is 0.465. Now Oswald efficiency factor he has assumed as 0 0.8. Okay, so then he has calculated CD naught. So over here you will see that he has used a ratio called S wet by S reference. Okay, so actually see how has he calculated the CD naught. So first he has chosen the aerofoil over here, okay, which is Naka 6 series aerofoil. So the aerofoil has all of these parameters, right? It has the CL naught, it has the CL alpha, it has CD naught. So these parameters are given with the airfoil data. So with that, what you can do is you can take the CD naught of the aerofoil. Okay, but the problem is that the aircraft consists of many other parts. Okay, the aircraft is not only the wing; it also has fuselage, it has tail. Okay, so it has a rear tail also. Okay, tail at the back also. So because of this reason, the CD naught increases. Okay, and it increases by this ratio, which is uh, called like the wet surface area by the reference surface area. So the wet surface area is the surface area of the entire aircraft. Okay, so S wet is surface area of entire aircraft. So this will include wings, fuselage, horizontal tail and vertical tail. And S reference is the wing surface area. So this ratio, it comes out to 3.5 in this case. So therefore the CD naught is 3.5 into CD naught of the wing, of the aerofoil. So this one is 0.0055. This is the CD naught of the aerofoil. So from here you get that the effective CD naught of the aircraft is 0.02. You can also calculate the K. The K will be 1 by pi aspect ratio E. Okay. You know that the aspect ratio is 6 and E is 0.8. So from here you can also calculate K. Now when it comes to wing loading for climb, so acha, Q also he has calculated. You can calculate Q as half rho v square. So he has assumed the climb speed as 70 knots and he has assumed that we are flying at sea level. So Q also you can calculate, which comes out to 16.6 pound per feet square. Now for the wing loading at climb, you can use uh, this. You can use this formula over here. So you see, he has put T by W minus wing gradient plus thrust loading minus wing gradient minus all these terms divided by these terms. So from here you get W by S is 62. Required W by S for climb is 62. Now we come to the cruise section. So hmm, so for the cruise section, the cruise velocity is given. Okay, so over here, if you see that the cruise velocity is given as 115 knots, and the cruising altitude is also given as 8,000 feet. So with these parameters, you can calculate the dynamic pressure for cruise. So the dynamic pressure comes out to 35 pound per feet square, and this aircraft is optimizing for range. So then you can calculate the wing loading like this. So the wing loading for cruise is Q pi aspect ratio E CD naught. So you put all these values and you get that the wing loading is 20. So what we find from here is that uh, for different phases of flight, okay, we are getting different kinds of wing loading. So for the stall condition, the wing loading is 10. So let me write over here somewhere. So for stall 10.2, and then for takeoff it is 14.9. So these are the different wing loadings which we require. So out of these, okay, uh, usually we try to select the lowest wing loading because uh, then there is less stress on the wing. Okay, I mean, see, we have to now see what thing we have to give priority to. Okay, out of these things. Okay, now I feel that the we have to give more priority to the stall and the takeoff conditions because uh, if these things are not optimized, then the aircraft won't be able to take off itself. Okay, and after takeoff, you will see that the climb phase, it requires 62 wing loading of 62, which is very high. Okay, now if we do not like if the wing loading condition is not satisfied in any of these phases, then it won't be efficient. Okay, so it will not be fuel efficient, or there might be some other trade-off, like then we might not have be able to fly at our desired velocity. Okay, or we might not be able to fly at our desired altitude. Okay, so all these things are there, but I think that the takeoff parameters are more strict. Like we have to take off at some distance only, like we cannot expand, like the takeoff distance is usually not flexible, and the takeoff velocity is also usually not flexible. Okay, but the climb rate and the cruising velocity, cruising altitude, these things are usually more flexible. So therefore I think that we have to give more priority to the stall and the takeoff conditions, and therefore we select the lowest wing loading out of this, which we get a wing loading of 10.2. Okay, and you will see that this is similar to the other aircrafts of the same category. So as you saw over here that some other aircrafts of this same category, they have wing loading of 10 and 10 plus minus 3. So since our aircraft is also of this kind, we it should not be too different, right? So therefore we select the 10.2 wing loading. But now I will solve some exercises. So this is the first exercise. So this one is quite simple. So here you need to know the ratio that the touchdown velocity is approximately equal to 15% more than the stall velocity. So then you can calculate Vs as VTO by 1.15. So this comes out to 247.82 kilometer per hour. Then you can convert it to meter per second. To get 68.84. Moving on. So this is the second question. So over here you have to draw the, so this is the, this question talks about the landing phase, I mean the approach phase. So you have to draw the free body diagram here. Now if you split the components along the thrust drag axis, you will get that thrust minus drag plus weight sine gamma is equal to 0. So therefore you will get thrust is equal to drag minus weight sine gamma Okay, sorry. So you get that weight sine gamma is equal to drag minus thrust, and therefore sine gamma is equal to drag by weight minus thrust by weight. And here you can assume that the weight is equal to the lift. So you will get this is 1 by L by D minus T by W. Okay, this is sine gamma. So we know that aerodynamic efficiency is 10 and thrust to weight ratio is 0.05. So you can write 1 by 10 minus 0.05. So therefore sine gamma comes out to 0.05. So since this is a small angle, so gamma is also equal to 0.05, but this is in radians. So then you can convert it into degrees. So this comes out to 2.865 degree. Hmm. So this is the approach angle in degrees. This is the next question. So this question is also about approach and landing. So if you draw an aircraft like this, so usually it follows this kind of a curved landing path. Okay, this is this maneuver is called the flaring maneuver, and this is the flaring radius. This is the approach angle, and the approach angle is also the angle at this point. Okay, so this is also the approach angle, and this is the flare distance, and this flare distance is equal to r sine of the approach angle. And now sine of the approach angle, as we saw from the previous slide, it is 1 by L by D minus thrust by weight. So this is 1 by 10 minus 0.05. So this is 0.05. Sine of approach angle is 0.05. So the flare distance is then r sine theta A. So this is 500 meter into 0.05. So this comes out to 25 meter. So this is the flare distance. Moving on. So this is the next question. In this question, the answer is elevator, rudder, and throttle. So you know that during takeoff, we have to use the elevator to pitch up the aircraft. So the elevator is the control surface located at the back. So if this is the CG, then the elevator causes a downward force which pitches up the aircraft. Okay, so the elevator is definitely required, and of course, like you will require the throttle because the throttle is going to provide the thrust, right? So the throttle signal is required, and the rudder is also required in case there is crosswind or it is aircraft is off center from the runway. So this is the aircraft, okay, and if there is a crosswind from like wind coming in from the side, then the rudder is required to stabilize the aircraft on the runway. So the rudder is also required, but usually the aileron is not required because the aileron is meant for rolling the aircraft, and the aircraft it cannot roll on a runway, right? It cannot roll. So during takeoff, the ailerons are not used. Now this is the fifth question. So here the answer is less than 1. This is for normal kinds of aircraft. You can have special aircrafts which can have more than 1 thrust to weight ratio, but for most of the aircraft, the thrust to weight ratio is less than 1 in climb flight. So again, if you draw the climbing uh, hmm. So for most aircraft, the climb angle is very low. So climb angle is less than 30 degrees. So the sine gamma turn, it is also less than zero point 0.5. So sine gamma is less than zero point 0.5, and the lift to drag ratio, it is on the order of 10. So 1 by L by D, this is on the order of 0.1. So the thrust to weight ratio, it like at maximum, like for normal aircraft, the maximum thrust to weight ratio is on the order of 0.6. Okay, it is usually not more than this, and in fact, it is lower than this. Okay, it is quite lesser than this. But you have some kinds of military aircraft where the thrust to weight ratio can be more than one also. So you can have an aircraft which is climbing vertically up like this. Okay, you can have aircrafts which are climbing vertically up like this also, and also accelerating. So, but those are special aircrafts. Okay, so that is it for today. So thank you for joining today's session.